Hello, this is Eric from UNC Charlotte, and today we will talk about collective communications, the preferred way for MPI processes to communicate to solve a global problem. Collectives are global operations that involve all the processes in a communicator. There are about 60 functions in the MPI4 standard that provide collective operations, though we really need to only understand 4 of them, since the other ones are essentially variants on the 4 core methods. Broadcast is about taking a piece of data stored in one process and communicating it to all the other processes. Reduce is about aggregating partial results in different processes into a single process. Scatter is about splitting an array stored onto one process on all the other processes of the application. And gather is the opposite operation, where small pieces of an array stored in different processes are aggregated onto a single process. The collectives could be implemented with many local point-to-point communications. The good thing about MPI collective operations is that they let the programmer focus on the structure of the application. And the MPI implementation can provide the best way to execute the collective for the platform you are currently running on. MPI Bcast provides the broadcast feature. It takes 5 parameters. The first 3 describe what is being broadcasted, where the data that is being broadcasted is in memory, how many elements are being broadcasted, and what type these elements are. They are constantly defined to identify primary types, and while one could create custom MPI data types, this is an advanced feature of MPI. The last parameter identifies in which communicator the broadcast happens. At the end of the broadcast, all the processes of the communicator will have the same value. They will have the value that was originally stored by the root of the broadcast, the process identified by the force parameter. Let's look at the simple code that uses broadcast to understand how it works. Every process sets up a vector of 12 elements and fills it out with values which are different for each process. Then, a broadcast is executed from rank 0 of the world communicator. The broadcast consists of vec-size integers which are stored in the vector. The code prints the content of the vector before and after the broadcast. Let's run the code with each different process reporting in a different window to see what happens. We can see that before the broadcast, all processes have different values in the vector, and after the broadcast, all the processes have the same vector. Note that it is the content of the vector on rank 0 that is now in all processes, because rank 0 was the root of the broadcast collective. MPI reduce reduces an array of values from the different processes of the communicator onto the root of the collective. The communicator and the root are identified by the last 2 parameters. The data being reduced is stored at the address given by the first parameter, and the data will be reduced on the root at the address given in the second parameter. The third and fourth parameter indicate how many elements are in the array and what their types are. The fifth parameter enables to choose what type of reduction will be applied. There is a predefined list which includes the classic like sum, min, and max. But MPI also supports user-defined operators as a more advanced feature. The reduction code is fairly similar to the broadcast code. A vector is initialized with different values on the different processes. Then, the vectors are reduced onto process 0 of the communicator using a sum. When running the code, we can see that before the reduction, all the processes have different values in their first vector. After the reduction, process 0 has a vector of the same size that contains the sum of the values that were stored by the processes. Note that the output vector has been left untouched on processes which are not the root. MPI gather brings data from the processes of a communicator onto the root of the collective. They are identified by the last 2 parameters. But MPI gather does not reduce the values, it concatenates them into a larger array. The first 3 parameters identify where the array to be sent is located on each process, how many elements it has, and the type of data to be sent. The next 3 parameters indicate where the root will receive the data, how much data it is ready to receive per process, and the type of that data. The code creates 2 vectors, one to be used as a source array and one to be used as a destination array. The destination vector has to be longer than the source vector, because it will contain the data of the array from all the processes. After the gather happened, the process that routed the collective now has the concatenation of the data sent by each individual process. The output vector of the other processes have not changed. MPI scatter is the opposite operation to MPI gather. The communicator and root of the collective are identified by the last two parameters. A large array that will be split is stored at the root of the collective and is identified by the first three parameters. Note that the second parameter is the amount of data to send to each process, not the overall amount of data to send. Each process will receive a piece of that array in a buffer identified in parameter 4, 5, and 6. In the code, the source vector is the longer vector, since it is the vector that will be split among the different processes. After the scatter, the data that was stored in the root process of the collective has been split onto the different processes of the collective. We presented 4 collective operations. There are many more in MPI, but they are essentially variants on the core 4 collectives. The rootless collectives usually have their name start with all. They are rootless because there are no special process. In all reduce, all the processes get the reduced vector, and in all gather, all the processes receive all the data. MPI gather and MPI scatter require the data to have the same size on all processes, and the V variants enable to specify for each process how much data needs to be communicated. All the collectives are blocking in the sense that all processes need to have reached the call to the collective before the execution can continue globally. There are asynchronous versions of the collective, which are identified by the prefix I. MPI supports collective operations to coordinate the execution on the different processes. While there are many collectives, they usually fall in 4 categories: broadcasting data from one process to all processes, reducing data from all processes onto one process, scattering data from one process between processes, or aggregating data from all processes onto one process. Programming with collective is one of the easier ways to program distributed memory machines because it is easy for the application to maintain process symmetry. All the processes execute the same code and can be programmed as if the process executes the application in lockstep. While process symmetry helps with debugging, it is not foolproof. If one process calls a collective operation, all processes have to call the collective with parameters that are globally consistent. Otherwise, undefined behavior will happen.